It's unfocused. Okay, so let me share the screen. Here's where we were, and we're sort of just about at the level where we're going to pull everything together and stop this complicated discussion of trying to expand our vector space and worrying about what sorts of eigenvalues count and eigenvectors. So we were talking about this liberal interpretation of, going through an example of an operator that has a continuous spectrum. So simplest one might be the momentum operator. So that's why we're sticking with that. So trying to find the eigenvalues and eigenvectors of the momentum operator. And at least superficially, initially, we said, well, just going through the motions, solving the differential equation, here's the solutions, and there's no reason that we shouldn't allow all complex values of P as our eigenvalues corresponding to these eigenvectors or eigenfunctions. Means the same thing. But we decided that if we're going to try to eliminate solutions that diverge exponentially or diverge badly as you go to the left or to the right, positive infinity or negative infinity for x, any complex part of this, in other words, any imaginary part to P causes a problem. And so the restriction to the eigenvalue P being real kind of solves our problem in that, if none of these functions are ever going to be normalizable in the normal sense, but at least we get functions that have a finite inner product with perfectly normalizable functions that are in capital L2, if we restrict the eigenvalues only to real values of the momentum. And so therefore, in this sense, we can say the on this rigged Hilbert space, the eigenvalues of a Hermitian, or at least in this particular case for this operator, the momentum operator, the eigenvalues are real. That's the meaning of that. That if we want sort of non-divergent solutions to be our eigenvectors, then the eigenvalues have to be real. And that happens generally for more complicated operators, although a lot of times it's hard to solve for the eigenvalues and eigenvectors. Okay, so we're saying property one, which we proved for the discrete spectrum case, in which case our eigenfunctions were all normalizable. We showed using the proof yesterday that the eigenvalues are real for any Hermitian operator. And now we're saying the same thing is going to be true in the continuous spectrum case. Because if you don't force them to be real, you're going to get the kinds of associated eigenfunctions that are not in the rigged Hilbert space. And some of your inner products that you'll want to find out won't be defined. Similarly, property two, I think this is where we ended. Property two was something about eigenfunctions corresponding to different eigenvalues of a Hermitian operator are orthogonal. And so again, just following this set of, we're sort of following what happens for the momentum operator, which has a continuous spectrum. If we take the inner product between two of those eigenfunctions for different eigenvalues, P and P prime, we get something that looks like a formally divergent integral. And, but the argument we made before, when we were first talking about Dirac orthonormality, is that this product, even though it's formally divergent, we can make sense of it in terms of a delta function. And so this Dirac delta function, delta of k minus k prime, would be the inner product between these two functions. And that motivated having this normalization value 1 over root 2 pi out in front, even though formally e to the ikx isn't normalizable. With putting that 1 over root 2 pi in there makes this exactly a Dirac delta function. So in this case, this gives something that is almost a Dirac delta function. We haven't chosen our normalization constant a. We put an arbitrary a out in front of it, and we might wonder, well, what should we choose a to be? Well, it looks like if a is 1 over root 2 pi h bar, then we've solved it, right? I'm not going to go through this stuff, but there's something about manipulating delta functions that I don't want to talk about right now. If we choose that normalization constant to be 1 over root 2 pi h bar, then the inner product between the eigenfunction corresponding to p and the eigenfunction corresponding to p prime is exactly a delta function, delta of p minus p prime. And I noticed this, I put this in red because in my notes, this was mistakenly written as delta of x minus x prime, but it should say delta of p minus p prime. Of course, we integrated over x there. There isn't any x's left in here because this inner product is an integral over x. Okay, and again, that's Dirac orthonormality. It looks sort of like the inner product between, psi m and psi n is delta mn. This is the same thing, but with a Dirac delta function, 0 unless p is equal to p prime. If p is equal to p prime, we get infinity, but that's the closest thing we can get. Okay, so that's the first two properties. Eigenvalues of a Hermitian operator are real. We're saying there's some analogous property for continuous spectrum cases, operators, Hermitian operators that have a continuous spectrum. Functions corresponding to different eigenvalues are orthogonal. And then property 3 was that the collection of those eigenfunctions that are on the rigged Hilbert space is complete in the sense that any function that is actually square integrable can be written as a linear combination of them. And when we say a linear combination, here we have a continuum of these functions. So we have a continuum of coefficients, and summing goes to integration. So for us, that's saying that when we do this, let's see, our functions fp of x, we use the normalization I indicated on the previous page. The normalization is 1 over root 2 pi h bar times e to the I px over h bar. And the question is, how do we find those coefficients? The answer is exactly the same way we did before, right? When we asked, how are we going to find the coefficients, just to remind ourselves, and oh boy, this video really won't focus unless I stop and start the camera. Let's remind ourselves, if I have some psi arbitrary shape, I usually write that as psi of x and 0. And I want to write it as a linear combination of, say, simple harmonic oscillator eigenfunctions. How do we find those coefficients? What was the process we go through? Yeah, I multiply by psi m star. In this case, they were real, so I didn't really need the star. But in general, you'll need a star. And we're talking about some functions here that we found that are complex exponential functions. So I really do need to keep the star in there. And then we integrate it over all x, right? Here, this stuff doesn't depend on x. The first stuff that starts depending on x is right here. So the integral can be moved into there. And the key thing is that these were orthonormal. And so I can write this whole integral, this inner product, as delta mn. And then we said we have an infinite series here. But all of the terms of the series are going to be 0 for all different n's unless n is equal to m. And when n is equal to m, this is 1, and this would have the value cm. So the right-hand side totally simplifies down to cm, and that tells us the formula for cm is this, or the formula for cn is just the same thing with an n placed there. Let's do the same thing for the case at hand. Let me just go below here, and we'll see that we're doing exactly the same thing. I've got my Dirac orthonormalized set of eigenfunctions, and I want to write a perfectly square integrable function as a linear combination by integrating over all p values, momentum values. My coefficients here, I'm just using the same kind of notation, but it's not a function. There aren't a discrete collection of coefficients, but a continuous collection of coefficients, times our normalized Dirac orthonormalized set of momentum eigenfunctions, e to the I px over h bar. we're summing them up for all the different p values. We've got a continuous index that we're summing over there. And the question is, how do we find what C of p is? Well, maybe it'll be simpler if I just, I'm going to denote this whole function like I'm doing in the notes by f p of x, okay, just to make my integral. And we're going to remember that these functions are Dirac orthonormalized. This is f p of x. What do I do to find these coefficients? Well, we're going to do the same thing. We multiply by the corresponding function starred corresponding to a different eigenvalue. And on both sides, fp prime of x. And we integrate with respect to x. So we integrate from, we got two integrals going on here, so I'll put the integration index. Here I'm going to integrate from x equals minus infinity to infinity. This stuff just depends on p, so I can bring my x integral in here. Integrate from x equals minus infinity to infinity and put my dx there. And what is this quantity? It's a delta function because we've already Dirac orthonormalized these functions. This is delta of p minus p prime. And that's great. Just like this Kronecker delta kills off the sum, the Dirac delta function kills off the integral, right? We know that when you integrate a delta function next to some other function, you just evaluate this function at the place where the peak is of the delta function, where it blows up. Okay, so this thing is delta of p minus p prime, and then I do the p integral and I get c of p prime. And then I say, well, I wanted c of p, but of course that means that c of p is just the integral from minus infinity to infinity of fp of x, psi of x0 dx. I forgot my dx here. Okay, so same thing. That's called the Fourier trick, at least by Griffiths, because you use it in Fourier analysis or Fourier analysis, depending on how you say it. Okay, so that's what is summarized down here. Solve for the momentum, the coefficients in that expansion in momentum eigenfunctions is easy as long as you've Dirac orthonormalized them, and I get a formula that looks like this, and that's telling me how to solve for c of p prime. And in abstract notation, I've wrote it explicitly here in terms of x, functions of x, but in abstract notation, we could just say, what do you do to find c of p prime? I take my function x, or what I called psi of x0 here, and take its inner product with that eigenfunction, fp prime. Or if I wanted c of p, I would take the inner product with fp. Here it is written explicitly in terms of an integral. Okay. So just to summarize that, those three properties, the argument's a lot more complicated, but we can make it work on this rigged Hilbert space and allow this more general set of eigenfunctions that technically aren't normalizable. And those three properties having to do with reality of eigenvalues of a Hermitian operator, orthogonality when you have different eigenvalues, and completeness of the set of eigenvectors or eigenfunctions, okay? We just demonstrated it here for one operator, but it works for the other operators that we've encountered with a continuous spectrum. For example, we had a continuous part of the spectrum in the Dirac, free particle is essentially, it works the same way. Dirac delta function potential had a continuous part, and the finite well had a continuous part. So with much more effort and a lot more thinking, you could show that the same kind of things happen there. All right, any questions on those kind of three important properties? So in summary, Hermitian operators have real eigenvalues, eigenfunctions corresponding to different eigenvalues are orthogonal, and the collection of functions is complete. Now, there's one Hermitian operator, which is the simple operator x, which means multiplication by x if we're talking about functions of x, that is a little bit strange. And so let's talk about, and you read about Griffith's arguments here for how to find the eigenfunctions of the x operator. For the momentum operator, we had to solve a differential equation because the momentum operator is a derivative operator. But we get something unfamiliar when we're talking about the position operator. So let's find the eigenfunctions and eigenvalues of the position operator, which, at least if we're talking about the position representation, where we're representing states as functions of x, it would be represented by multiplication by x. That's the way we've been thinking about it so far. Okay, so let's write down our eigenfunction. You know, we're going to write down q hat times some fq of x is equal to q times some fq of x, and try to solve it. And for the momentum operator, this was a differential equation we had to solve. For us, it's going to look like this. I might write it as, let's see, what notation did I use here? X times some function of x is equal to a particular, no, yeah, I might even, well, let's just call it x0 times that same function back again. So here's my operator operating on this, gives a particular value, and I just happen to be calling it x0 times that. And we might then say, well, okay, if the eigenvalue is x0, why not label this function as the eigenfunction associated with x0? So I'll put a little x0 subscript on there to indicate that. Okay, how do we think about this? Well, one way to think about it is I've got something multiplying g of x on both sides. I could just put everything on one side and put a 0 on the other side, and let's think about that. So that would be x minus x0 times this function that we're looking for is equal to 0. Let's think about what that means for that function. It's not a differential equation, but it is constraining that function. And the one thing I know when I see this is that I've got a product of two things equaling 0. And algebraically, that tells us a lot. That tells us that either one factor is 0, either this function itself has a value of 0, or x is equal to x0, right? That would make this factor 0. So in other words, it's saying the eigenfunction we're talking about is 0 everywhere except at the value x equals x0. So that's a little clue. Let's try to draw that. I'm trying to draw gx0 of x, the eigenfunction that goes along with the eigenvalue x0. And here's x0. We've just found out that it's got to be 0 everywhere except at x0. Okay, that's pretty restrictive so far. Now, what about the value at x0? We got to remember our context is we are in a rigged Hilbert space, so we could consider normalized functions. They might be eigenfunctions. What if I put a value 0 at x0? Well, it's not going to be normalizable, right? Its normalization would be 0. What if I put a finite value at x0? It's still not normalizable. It's just as good as 0 because the area under the curve is still 0. So my only option is to think about some other functions, some weird functions, and they're not even functions at all, that I've added into my rigged Hilbert space. In addition to functions, you know, when I talked about what we're adding on to capital L2, in addition to functions that are square integrable, we added in functions that don't diverge as you go off to plus or minus infinity. So they have a finite inner product with functions in L2, and also delta functions. And so my only hope is that, you know, somehow this is like something that has an area 1 under it, but gets really tall there. If it goes to a finite value, we're out of luck. It's not, it's the area under the curve is 0. But if this goes up to an infinite value, I could sneak an area of 1 under there. So it seems like G, this eigenfunction that corresponds to eigenvalue x0 should be something like delta of x minus x0, right? You might worry about the normalization, and it's sort of complicated to think about it because, you know, when I normalize it, I have to take the integral of a square of a delta function. I'm not going to comment on that at all. Now, so here's our potential eigenfunction, and notice that if I have a delta function here and I multiply it by x, since this function is 0 everywhere except at x equals x0, this would have the value x0 there, and so it reduces to the right-hand side. And so it solves this in kind of a degenerate or trivial kind of way, solves that equation. So this is our eigenfunction. And the corresponding eigenvalues, we haven't found any restriction on what x0 can be. x0 could be any real number. So the associated eigenvalues are any x that's real here. Now, I guess I shouldn't be so flippant here. Why not? Why can't we have complex x's? I mean, I'd like to be able to conclude something about the 3 properties in this case. And the first one is that these eigenvalues have to be real. What if x0 were I? You know, it's just a number I put in here. What if x0 had the value I?
Well, first of all, even if we were to assume that that could happen, I would imagine, pun intended, that we wouldn't be able to observe it at all.
Yeah, I mean, I'm not sure how to think about, you know, what that would mean physically, but just speaking mathematically here, suppose let me just mess this up for a second. Let me put an I there. Now, what kind of variable is x? Can it have complex values? No.
Oh, no.
X is the real number axis. So as x goes from minus infinity to infinity, are we ever going to hit the point where this is non-zero? Okay, so if x has any complex or any imaginary part to it, and if it's not real, then this function is going to be 0 everywhere on the x-axis, and it's just as good as the function 0, and it wouldn't be normalizable, right? So we can't take that as the 0 vector can't be one of our eigenvalues. So this value, I should have said x0 here. Our x0 values have to be real numbers. Okay, so that's a demonstration that x0 has to be real. Otherwise, we're talking about the corresponding function is just the 0 function, which is the 0 vector, which isn't an allowed eigenvector. Okay, the second property that we'd like to demonstrate, our property 2, is that eigenfunctions corresponding to different eigenvalues are orthogonal. And here's what Griffiths says. It's a little bit suspect, so you might want to just think about how to sharpen it up a little bit, because the property of delta functions we're going to use isn't justified here. But so I want to show that eigenfunctions with different eigenvalues, I'll just write that as evals, are orthogonal. That was our second property. Let's check that. We found our eigenfunctions here. Griffiths writes it this way. I'll follow the notation he does in the book. He says, well, that means we have to take an inner product. How we take inner products with functions of x is we integrate from minus infinity to infinity. this function, I don't necessarily need to put a star on. It's a perfectly real function. There's no imaginary part to the delta function. So I can just write it as delta of x minus a particular value, Griffiths calls it y, times delta of x minus y prime. Here we're talking about two different eigenvalues, y and y prime, and these are their corresponding eigenfunctions. No star needed. And here's what Griffith says. Well, you know, when you're next to a delta function, what you do is replace the value of x in the other function that's next to it with the place where this one blows up. So nominally, this is equal to a delta of y minus y prime, which is certainly 0 if y is not equal to y prime. Now, you should be a little bit suspicious of that, because what we proved is that if you put a delta function next to a continuous function, that you can do this kind of manipulation. This is certainly not a continuous function, so it's suspect. Now, you can justify this by saying, well, let's not use a delta function. Let's use an approximation to a delta function, you know? I'm not going to go through the argument, but you can make this argument rigorous. Let's say, let's take an approximate eigenfunction, you know, that's centered on a value y0, and it's only non-zero between y0 minus epsilon and y0 plus epsilon. And to make my life easy, I'm just going to make it go up to a finite value between there. That's an approximation to a delta function. And you've got to choose the height of this function to, you know, of course, the smaller epsilon is, the higher this function is going to have to be. So this is going to be proportional to 1 over epsilon. But you got to normalize the function so that when you take the square of this, you get an area 1 under the integral of that curve. And then take two of those, one centered at y, one centered at y prime, as functions of x. This is as a function of x here. And you can actually demonstrate that this is true. But I'm not going to go to it now. So even though it looks like this is illegal, you're not supposed to do this kind of manipulation because this has to be a continuous function to do that. It still goes through if you approximate a delta function by a very narrow, very tall function that has an area under the curve, under the square of the curve that's 1. Okay, finally, for completeness, and just for the sake of the Zoom folks, let me continue the discussion up above here. So number 3, our third property was completeness. And that means that I should be able to write any arbitrary square integrable function. So I'll just say this is in capital L2 as a linear combination of of eigenfunctions that are centered on that value, and we're going to sum over all y values, and the y values go from -infinity to infinity. That's the claim. I should be able to write an arbitrary square integrable function as a linear combination of these, and this one's centered at y. We've got a different one for each y, so we got to sum them up over all y's. And how do I solve for the c of y's? The same way we did before. If I put this dy over here, what we do is, to solve for c of y, we multiply both sides by delta entered at another x value, delta x minus y prime, and then we integrate with respect to x. And again, you kind of have to hold your breath here, but we're going to say that this is delta of y minus y prime. And then that delta function kills off this other integral and just leaves c of y prime. Okay, and on this side, let's see, I didn't finish my thought here. This was integrate from y prime, integrate from x equals minus infinity to infinity dx. That's what I did on the other side. Now, in this case, I don't have to leave the integral because I've got a perfectly normal function of x next to a delta function. So let's just do that. And when I do this, I just evaluate this function at x equals y prime. So this side simplifies down to f of y prime. All right, so what I found out is that c of y prime is equal to f of y prime. In other words, c of y is f of y. And perhaps that's not surprising when you think about what we're doing here, writing something as a linear combination of delta functions. The coefficients are, in fact, those, well, the coefficients that are needed are, in fact, those, let's write it out. What I said was, I want to write an arbitrary f of x prime as a linear combination of delta of x minus y summed over all y, and I want to put my c of y's here. And the claim is the correct thing to do is to put an f of y there, right? And then integrate from y equals minus infinity to, yes, f of y there. And then integrate with respect to y, and this should be a prime there. And when I do that, of course, the right-hand side just simplifies down to f of x. So it makes it true again. So the expansion coefficients here are kind of trivial. You could have just by staring at it almost guessed what they had to be without using the Fourier trick. But I can write any arbitrary square integrable function as a linear combination of delta functions in this particular way. And the coefficients are just the value of that square integrable function itself. Okay, so what that demonstrates is, this is a weird eigenvalue equation, but we've demonstrated that, again, it's a continuous spectrum case. The spectrum here is all real numbers. It's real. This is a Hermitian operator. We're expecting the spectrum to be real if we want normalizable functions. And again, the three properties follow through. So this is a second example. Even though we're claiming it's true in general, we haven't proved it in general, but you're seeing that it seems like it's going to generally work. All right, any questions before we look at this worksheet? And I'm going to make you think through this kind of weird non-differential equation yourself. The worksheet is asking you, saying, well, we just did one function of x. So my operator I was concerned with here is the operator multiplication by x. Here in 1, we want to consider the operator multiplication by x cubed and find out what are the corresponding eigenfunctions and their associated eigenvalues so that we get perfectly so that we get reasonable eigenfunctions out. And then a slightly more subtle case, you might think it would be less subtle, but multiplication by x squared requires a little bit more thought. So take a look at that, struggle with it for a few minutes. We can talk about, well, I take it back. Let's do A together. And then I'm going to let you think about B for a few minutes and see if you can figure out what the difference is. Because it may be hard to get the idea if we don't do A together. So let's try it. The question is, find all eigenfunctions and associated eigenvalues of the operator multiplication by x squared. Okay, and multiplication by x cubed. Yes, we're doing A together. Thank you. So the eigenfunction, eigenvalue equation would look like this. X cubed multiplied by some function of x is a number. I'm just going to call that number y because it's sort of similar to what Griffiths calls, how he denotes it. And it's tempting to label these functions, this will be the eigenfunction associated with the eigenvalue y, and we want to know what values of y are going to be allowed. Certainly, this is a Hermitian operator. Any function of just x, a real function of x, will be a Hermitian operator. The same argument goes through that we used for x to show that it's Hermitian. Okay. Now, we can do the same kind of argument we just did before, right? I would say, let's put everything on the left-hand side, and I get x cubed minus y times fy of x is equal to 0. And that means either this function is 0. The only case where it might not be 0 is where x cubed equals y. Either fy of x equals 0 or x cubed equals y, and that has a simple solution. The x value where it's not 0 is going to be the cube root of y. Okay, so that means this function fy of x as a function of x, except at this value, the cube root of y is going to be 0, right? Same argument as before. This can't be any finite value at that one point, or it would be just as good as the 0 function. It's not, there's no way to normalize it. There's no way to associate any probability. Probability density would be 0 everywhere. And so the same kind of argument is that it's got to be a delta function there. Okay, so our eigenfunctions are going to be delta of x minus the cube root of y. What about the eigenvalues? What range of eigenvalues y can I take? Well, you can take cube roots of negative numbers and whatnot, right? I'm not allowed to put any, if I put any complex numbers in here, the cube root, you'd have to think about that. The cube root's still going to be complex. And then this function would just be 0 everywhere on the real x-axis. So the restriction is that y can be anything between minus infinity and plus infinity. Has to be a real number value. So I get a continuous spectrum again, not surprising, just like before. And then if you go back here and look at that, if this is a delta function where, well, let's write it down again, just to check, because, there's a little bit of strange reasoning here. If I put delta of x minus the cube root of y and try to simplify that, I would say, well, look, this function is 0 everywhere except where x is the cube root of y. So I may as well just put in x equals the cube root of y over here. I can equally well replace this with x equals the cube root of y, because this whole thing is 0 everywhere else. Of course, it's going to, still be 0 there. So I may as well just replace this with the cube root of y cubed, which is y. And that's the eigenvalue equation we were trying to find a solution to. Sort of a weird way to solve it, but that's what it is. So our eigenfunctions are this, and the eigenvalues we decided after thinking about it had to be real y eigenvalues. Take a cube root of a complex y, you get another complex value out of that. Okay, we're also supposed to answer, is the spectrum discrete or continuous? It looks like in this case it's continuous, right? Spectrum means just characterizing the set of all eigenvalues. Is it degenerate or non-degenerate? In other words, is there ever an eigenvalue for which there are 2 corresponding eigenfunctions? And the answer is no. For every eigenvalue, there's exactly 1 eigenfunction. You're going to find out that that's not true in the case of multiplication by x squared. It's actually degenerate. So keep that in mind as you're trying it now. That's part B of this worksheet. Yes, it does. So we're missing Jake Woosley today. So the hint is you should be finding for each value of y, there are two functions that correspond to it. If we call the eigenvalue y again. Okay, let's just run through the logic again following this example. So I'm just going to erase my cube and put a square there, put stuff on the left-hand side and factor the same way I did before. Not too much different going here. And so the conclusion is either this eigenfunction is 0 or x squared has to equal y. And the difference is that there are two solutions here. That means that x equals plus or minus the square root of y. Okay, so that means I've got a function that might be non-zero at plus root y or a function that might be non-zero at minus root y. In other words, we're saying either the function is 0, let's say here's the value y as a function of x over there, either the function is 0 at x equals plus the square root of y, and same argument as before, we're going to need a delta function there to make it something that's just has 0 normalization, not have some 0 normalization. Or we get a function that's down here at minus root y, and it's 0 everywhere except at that value. Okay. So we might, we can call these functions delta of x plus root y and delta of x minus root y. Both of those linearly independent eigenfunctions correspond to the single eigenvalue y. There are two x values at which we might have that. Okay, so I could say for each y value, and in this case, what y values can I have? What's the spectrum going to look like here? Continuous, certainly, but what values of y are allowed? All real numbers? Yeah, it has to. We have to restrict to 0 to infinity because, again, I can't have something imaginary here because x is real, and therefore this would be 0 everywhere on the real axis, which we don't want the 0 vector as an eigenvector. It's not allowed. And therefore, I need to restrict this to make this value be real, and that means y has to be non-negative. So in this case, our spectrum is y has to be between 0 and infinity, a real number, and our corresponding eigenfunctions that correspond to that eigenvalue y would be a set of 2, delta of x minus the square root of y and delta of x plus the square root of y. And of course, any linear combination of those two would also be, you have two eigenfunctions corresponding to an eigenvalue. If you add them together, you'll get another eigenfunction that would be correspond to that eigenvalue, but it wouldn't be linearly independent of these two. So we have some choice about how we choose them, but conventionally, we usually choose them to have just the spike at one spot or the other. Okay, so in this case, the spectrum is continuous. The y values have to be non-negative. And the spectrum I would characterize as degenerate. Sometimes people call this doubly degenerate because for each value of y, there are two corresponding eigenfunctions. Except at 0, right? Down at 0, there's only one of these because these are the same function there. Questions about that? Functions of x are just an oddball case. If you really want to challenge yourself, you could say, well, what about if I took sine of x or something like that? Oh, well, just like the problem with x squared is it has the same output at two different x values. Sine of x has that problem over and over again. So you could think about there might be an infinite number of eigenvectors corresponding to an eigenvalue if you chose the operator multiplication by sine of x. It's a Hermitian operator, so certainly should have real eigenvalues again. That would be an interesting homework problem, but I don't think I did that one. Okay, that's the end of, wow, finally, section 3, and we're going on into section 4 now, 3.4. And this section is the culmination of all our work of discussing all of these kinds of strange properties and solutions to eigenvalue equations. What can happen in the most general case? So this is called the generalized statistical interpretation. It's what we've been waiting for. It's going to tell us how to find the probability density as a function of any dynamical variable. We already knew how to find it as a function of x. It was just psi star psi. Now, how do we do it as a function of P? How do we do it as a function of total energy E? How do we do it as a function of any other dynamical variable you can make up? So here's the statement. And this is where we're really postulating this at this point because there's some new information contained in the box here that isn't necessarily what was there before. So this is sort of sharpening up what quantum mechanics is telling us. If one measures the observable, so that I'm imagining it's an observable, so we're assuming the corresponding operator is a Hermitian operator. That's sort of unspoken here. Whenever you say observable, the corresponding operator should be Hermitian. When I don't put the hat on it, that just means the dynamical observable. So this could be some arbitrary function of x and p, as you know from advanced mechanics, that any function of the state is going to be some function of x and p. Okay, if you measure it in the state, some particular state of the particle, right? Normally we think of this as a psi of x if we're using a position representation. Then the outcome is certain to be one of the eigenvalues of that operator. So we've already seen that for energy, right? If you measure the energy of a particle in a particular state, then the energy you measure is certain to be one of the energy eigenvalues, which is the energy solutions to the time-independent Schrodinger equation. This is just same thing's true for other operators, like the momentum operator, like the position operator, for example. Things are slightly different depending on whether the spectrum of that operator is discrete. If the spectrum of Q is discrete, then the probability of measurement resulting in a particular eigenvalue and having associated with a particular eigenvector is, well, what do? You take your state that you're in and expand it as a linear combination of these orthonormalized eigenvectors, right? Just the same, the sum Cn times psi n kind of thing. And then the probability of finding it in any one of those eigenvector values is just the magnitude of Cn squared, the expansion coefficients, where the Cn's can be gotten from this inner product. That's the abstract notation for the formula we've solved for Cn many times now. So that's the discrete spectrum case. The continuous spectrum case looks almost the same. If the spectrum is continuous, and so in this case, we don't have discrete eigenvalues Qn, we would just say we have a range of Qs, a continuous range of Qs for which there are associated eigenvectors. And I'm just going to label the eigenvector that's associated with eigenvalue Q just as a vector with a Q in it. That's a nice efficient notation for it. Then how do we calculate the probability density as a function of that dynamical variable Q? What we do is expand, we say if there's a probability density, we got to be in some particular state. We expand that state as a linear combination of these vectors. Maybe they're functions of x if we're using the position representation. Get the expansion coefficients, and we take the magnitude squared of those, and we will get the probability density. So if you're talking about the position operator, we already found that if you're in a state psi of x0, the expansion coefficients are the psi of x0 functions already, and we just take the magnitude squared of those, and that tells us the probability density as a function of x is the magnitude of psi of x squared. But this tells us how to get it for momentum. If I want the probability density as a function of momentum, I have to expand my given state as a function of definite momentum states, get the expansion coefficients, which come from this inner product. That's from Fourier's trick that we've done a few times. And then take the magnitude squared of that, and that will give me a continuous function of Q, which represents the probability density. Okay? And then the last thing that sort of doesn't go along with this, but then the question is, well, what if I make a measurement of Q? If I make a measurement of Q, position, momentum, energy, those are the big three, then the wave function is going to collapse to the corresponding eigenstate that corresponds to the outcome of the measurement. So if I measure a particular value of Q, the wave function at that moment collapses to the corresponding eigenstate. Okay, so that pulls together really everything and adds, sort of a new level of expressiveness to quantum mechanics. And in other books, you would see those things expressed as postulates or introducing new postulates in quantum mechanics. Griffiths kind of hides it a little bit, but it's not necessarily a bad thing. Griffiths demonstrates, I'm not going to demonstrate here, that if you have a normalized wave function, then it will always be true that the sum over all the allowed expansion coefficients in the discrete case add to 1 for any dynamical variable and the associated operator. And if you find the area under the probability density function curve, it adds to 1. So once you normalize it, all the probability density functions that you could calculate are automatically normalized, which means you can, once you've normalized your wave function, you can just interpret things as probabilities in the most straightforward way. The expansion coefficients, a lot of times when I write down the expansion coefficients, it's as if they don't depend on time, and probably this is worth writing out again. We've been doing a lot of things where I've written down something that's like this. In our old energy kind of context, right, I would say, oh, at some time, I've got a state that looks like this at time t equals 0. And we're going to write that as a linear combination. Let's assume we're in the simple harmonic oscillator context. So the starting index is 0 there. We got some expansion coefficients times the psi n of x's. And, well, you might ask yourself, what happens as time goes on? Well, as time goes on, we know what to do with this. To introduce the time dependence in there, we put in this time-dependent complex exponential factor, e to the minus I e n t over h bar, right? And one way to think about this is you could combine this together with this and say, well, that whole mess is what we might call how Cn depends on t, right? Because we're getting the expansion coefficients as a function of this at all times. It tells us how they're going to depend. And it's the same way, for some other variable, right? If I have psi that's changing with time, at different times, I might have different expansion coefficients in front of the definite momentum states or definite position states or something like that. And so the expansion coefficients in general are functions of time. Although, we've been concentrating on finding them at one particular time, at least in the case of energy. So to do that, what you do to find those expansion coefficients as a function of time, you put in your fully time-dependent wave function and take its inner product with the function fn star, right? Integrate fn star of x times psi of x and t, integrate with respect to x, and the x's will go away, but you'll get something that's a function of time after you integrate over x. How do we find expectation values? Well, we already said earlier that Griffith sort of guessed the probability interpretation, at least in the energy case for these. And now we know these actually, we've just postulated in our generalized statistical interpretation that these all correspond to probabilities. And so if I want to find the expectation value of Q for any dynamical variable Q, I just sum the probability times the value over all allowed values. And similarly, if I want the expectation value for, in the case of continuous eigenvalues, I just integrate the probability density times the variable. And again, I noticed that in my notes, this was missing there. That's a typo. There should be a Q next to that under the integral, and integrate with respect to Q. Okay, that's the way, if we wanted to, just like we wanted to find the expectation value of x, we wrote the integral from minus infinity to infinity of the magnitude of psi of x squared times x dx. That's how it looked like for, sometimes we just put the x in the middle, but it's the same integral. All right, good. Let's just go through the example of momentum. I think we've done these things before, but let's find the expansion coefficients for momentum here. If you have as a, you're given a solution psi, which is a function of both x and t. So I've solved the time-dependent Schrodinger equation for some function of x and t, and I want to find out what the expansion coefficients are, not only as a function of momentum, but also as a function of t. And so in this case, I put the full time-dependent function in there. Here's our function of x with its normalization to make it a Dirac orthonormal state. I do that inner product. This was a function of x and t, but I integrate with respect to x so that all that's left is the t dependence. But there's also a parameter p in here that it depends on. So the resulting thing depends on p and t. And of course, momentum is useful. So these expansion coefficients, which we might have called C of p, are given their own notation. Griffiths calls it capital phi of p and t. It's given a special symbol and it's given a special name. It's the momentum space wave function, or the momentum representation of the state. And this is kind of like, we gave a psi of x and t over here, but there's no reason to be biased about x. We could just as well be biased towards momentum. And so someone might say, oh, the state of my particle at time t equals 0 is phi of p at 0. And everything would sort of look analogous to how we specified it in x, but you'd be giving momentum information instead of x information. So we call this the momentum space wave function, or momentum representation. But it also corresponds to a kind of Fourier transform of this function to get that. And once I have those expansion coefficients, we're claiming that if you want to find the probability that a momentum measurement is between some momentum values PA and PB, you just integrate from PA to PB of the rho of P under there. And so the claim is that's just the magnitude of phi of P and T squared. And maybe the probability of being between these two momenta might change with time. At some times there's a large probability between those two values. At other times, most of the probability is outside that range between PA and PB. Okay, and so now that we know not only how to calculate rho of P, but rho as a function of any other dynamical variable, we can calculate any statistic, any probability that we want as a function of any dynamical variable. So if you have any physical observable, you can use this process to calculate corresponding probabilities if you were to take a measurement at a particular time. Okay, so there's a second worksheet. This is the second one that's posted for today that is on this generalized statistical interpretation. And maybe while we're doing the worksheet, this is a little bit of a longer one. I'm going to flip back to the statement of the generalized statistical interpretation. I think this has both front and back sides. So we're going to take a little bit of time to work on it. So here you're given a state psi of x and 0, and you're supposed to find the probability density as a function of momentum at time t equals 0. You know the state at time t equals 0, you want to find the probability density as a function of momentum at time t equals 0. Why don't you work on the first page? There's a separate problem on the backside, and maybe we can stop and talk about how to think about the first page, make sure we're all in the same place, and then go on to the second problem. Okay, maybe we better come together and at least start doing this because, compared to the amount of time we've been doing this, there's not that much writing, at least here in the classroom. So let's think about this, and I'm just going to point to something here. We've been talking about the momentum operator, and this particular problem wants to know essentially what the probability density is as a function of momentum. So we're concerned with the momentum operator. And the momentum operator, as we've talked about, has a continuous spectrum. So I'm looking at this piece of the generalized statistical interpretation, and it's saying, if you want the probability density as a function of momentum, you need those expansion coefficients as a function of momentum, magnitude squared. And to get the expansion coefficients, you take the inner product of whatever your state is at time t equals 0 with the states of definite momentum. So let's go to the board here and see what I've written down. So we're saying we want rho of p, and that is the magnitude of the expansion coefficients squared. What do the expansion coefficients mean? I mean that you take the function that you're given and you want to write it as a linear combination, here's my coefficients, of these definite momentum functions, and we always want to use the Dirac orthonormalized versions. That's why I have that weird normalization constant out in front. Just take that on faith that makes it Dirac orthonormalized. And to find those coefficients, right, I'm saying sum over all p's with different coefficients for each p times the 1 for each p. And to find those coefficients, of course, we could use Fourier's trick, but you don't have to do that every time. We know that the generalized statistical interpretation says, take the inner product of your state psi that you're in here at time t equals 0 with a state of definite momentum. Okay, let's expand that out as an integral. It'll tell us what integral to do. That means whenever we do an inner product in this way, we mean an integral from x equals minus infinity to infinity. The thing that appears on this is a definite momentum state, but it's on the left, so it needs a star on it. So I get a 1 over root 2 pi h bar times e to the minus I px over h bar, okay, times our psi, which here is psi of x at 0. And we have to integrate with respect to x. And so I just start chipping away at that, right? Psi, I believe, was only non-zero for a certain small region, right? Psi was non-zero from x from minus a to a, and I already normalized psi for you. If we're going to interpret this way, you better be using a normalized psi, right? Because if psi is twice too big, these aren't going to correspond to probability densities anymore. Okay, but I gave you a normalized psi right there. So let's calculate this integral. These are the expansion coefficients. Up here I'm calling them C of p, but this is just a rebranding of C of p. It's the momentum space wave function at time t equals 0. So to calculate this integral, we can factor the 1 over root 2 pi h bar out in front. We don't need to integrate from minus infinity to infinity because our psi is only non-zero between minus a and a, right? And in between minus a and a, the value of our state psi at x and 0 is 1 over root 2a. That's just to normalize it. Okay, and what's left inside the integral is integral from minus a to a of e to the minus I px over h bar dx. Everybody okay with that simplification step? And that, we're not doing too many horrendously complicated integrals in here. This is an integral or antiderivative that I can do, right? Integral of an exponential function is an exponential function, but you need that chain rule in there, right? Because the derivative of this would pull down a minus I p over h bar. So when we anti-differentiate, we are going to need an h bar over minus I p times this same function back when I anti-differentiate. And then we've got to evaluate between minus a and a. Okay, so I still got those same constants floating out in front. Maybe we can try to combine all the constants together here. I've got some constants here and here and here. So it looks like I have a factor of 1 over 2 because I've got a pair of 1 over root 2's. I've got a root pi and I've got a root a in the denominator up here. I've got a 1 over root h bar, but then I have an h bar in the numerator. So that gives me a root h bar in the numerator. So I could write this as the square root of h bar over that, right? 1/2 times, oops, h bar. And I've got a p in the denominator. Let's put that down here. And a minus I in the denominator is just as good as a plus I in the numerator. Are you guys okay with that? Because I could just multiply numerator and denominator by I, and I times minus I is plus 1. Okay, it's taking some brain power just to combine the constants. All right, so now I'm going to have, let's see, let's evaluate at upper limit minus lower limit, right? I'm going to have e to the minus I p a over h bar minus e to the plus I p a over h bar. I'm just evaluating that exponential between the two limits. And this almost looks like a sign using, we're told the hint here is use Euler's formula. We know that e to the I theta minus e to the minus I theta over 2I is equal to the sine of theta. That's Euler's formula. And so we've almost got that. You know, if I multiply by 2I and then multiply by a minus sign to switch the order of those, then it would look like this. E to the minus I theta minus e to the I theta, tell me if I've made a mistake here, is minus 2I sine theta. Does that look okay? And that's kind of the thing we have here, right? The minus sign is coming first, and then we're subtracting off the one with the plus sign up there, and our theta is PA over h bar. So it looks like this thing in parentheses could be simplified. You know, it's sort of hard to think about this function, but I know how to think about signs. This is minus 2I times the sine of PA over h bar. Okay, and now I got some more constants I can combine. The 2 cancels out the 1/2. The minus I cancels out the I. That's kind of nice. Let's just write the final result over here. So the I and the 2 are gone. So it looks like I have a constant root h bar over pi a. Again, let me know if I'm making any algebra mistakes here. I'll check with my solution in a second. Times the sine of PA over h bar divided by p. I'm trying to put all the p dependents together. Remember, this is our momentum space wave function. So it's saying as a function of momentum, what does the state look like? Sine, okay, so that's phi. I still haven't answered the question. We want to find the probability density function, which is the magnitude squared of that, but that is phi of p at time t equals 0. And that actually is the answer to B. So along the way, we've answered B, right? What's the momentum space wave function at time t equals 0? That's phi of p at time t equals 0. Now, to answer the question in A, what we want to find rho of p, that's supposed to be the magnitude of C of p, or phi at time t equals 0 as a function of p, squared. So that would be, you guys hard to know if you can see this with the blurriness of the camera, but this is equal to just the square of this. H bar over pi a times sine squared PA over H bar divided by P. And in fact, I might even write this as PA over H bar in the denominator and get rid of those with just a factor of 1 over pi out in front. So this is like a sine squared x over x function. Yeah. Yes, you're right. That's the one thing I didn't square. So if P is squared, and I wanted to put this down here, this looks like this. Well, we can leave those over there. H bar over A. This looks like sine squared x over x squared kind of function, which is sine squared function is always non-negative. So rho of P, if we were to draw kind of a very rough graph of it, sine of x over x, you know what that looks like. Sometimes people call that a sinc function, right? It looks like this. Same thing on both sides, but we got to square that function. So when we square it, this is what rho as a function of P is going to be as a function of P. It's the square of this kind of function, which goes down to 0. Something like that. We could figure out the locations of those zeros and so on, but centered at P equals 0. Okay, and we answered B along the way. B just is this function. That's phi at t equals 0. And then finally, C, what's the probability of a momentum measurement at time t equals 0 yielding a value in the range between 0 and p0? Well, of course, the probability, this sort of goes back to the notion of how to use a probability density. It's the integral from p equals 0 to whatever that value p0 is of rho of x. So we just integrate h bar over pi a times sine squared p a over h bar divided by p squared. Integrate that with respect to p. And I don't know, I don't want to think about how to do that integral, but I said here you can express your answer as an integral. So if one could do that integral, or if you knew what a and stuff were, you could do this numerically, but there it is expressed as an integral. So that's the kind of stuff we're doing with the generalized statistical interpretation. Questions on that one? Check the time, 10:24. Okay. We got plenty of time to do this second one. We don't want to rush through this idea too quickly because we've already talked about energy as an operator in the energy spectrum quite a bit, but momentum is one of our other big operators, and then position is the third one. Those are kind of the big three that we keep switching between. We would like to know probabilities of position, momentum, and total energy measurements. And so this is an important thing to dwell on. So here's a second problem on the back side. Consider a particle of mass m in the infinite square well. Okay, I know what those psi n's look like if I need to use them. And it's in the initial state, which is a linear combination of the ground state and the first excited state. If you think about it, those 1 over root 2's out in front normalize my psi at time t equals 0. And we're supposed to find what that is as a function of time, and then find the momentum space wave function. And then again, the last step, you don't have to do too much work, but remind yourself what the probability is of finding this particle, in this case with a positive momentum. In other words, a momentum value that's going in the plus x direction. That still excludes all the cases where it might be heading in the minus x direction. So try problem 2, which is on the back side of the sheet.
Okay. Yep.
I'll write the energies and definite energy eigenfunctions up here just in case you've forgotten them. You might say, just to save a little space on the paper, even though, of course, it's just a linear combination of two states, but it sort of makes your life easier if you still write it as a sum over two n values like this, right? So here's my Cn for n equals 1 and 2. They're both 1 over root 2. And here's my psi n of x. And I'm writing it just as an explicit summation notation here, because otherwise I'm going to have a sum of two of these explicitly. It just takes up a lot of room on the page. And you'll find that the manipulations you're doing to both of those terms in there are the same. So you might try using summation notation just to keep your sanity. Okay, let's come together. This, I will warn you that B turns into a bit of a mess even with this kind of stuff here, but we'll try our best to write it explicitly out. Here's the given psi at time t equals 0. I've explicitly written out what the psi ends are for n equals 1 and 2. And the coefficients, which I could have put in here, are both 1 over root 2, and I'm just summing from 1 to 2, just to make my life a little bit easier. So that's what it looks like at time t equals 0. Now, if I want the momentum space wave function as a function of time, I need to use the position space wave function as a function of time. How do I insert the time dependence in here? Not to sound like a broken record. Yeah, we just take each one of these terms and multiply by the corresponding e to the minus I E N T over h bar, where I'm not going to bother substituting in the explicit formula for En. Let's just keep it there for now. Okay, so the formula for finding the momentum space wave function is just, well, the momentum space wave function is the same thing as those expansion coefficients. And in shorthand notation, this abstract vector notation, this is the inner product that we're told we have to do. Take the inner product for your psi at time t with a definite momentum state function, okay? So that means I need to, let's write it out and then we'll expand it even more. So this means in terms of an integral, it's an integral over x from x equals minus infinity to infinity. That's how we usually write out an inner product. A definite momentum state, when we Dirac orthonormalize it, that's 1 over root 2 pi h bar e. Well, let's see. Since this is on the left side of the inner product, I have to take the complex conjugate of a definite momentum state. So I need a minus I up there. P x over h bar. So there's our Dirac orthonormalized states of definite momentum, but starred because they're on the left side of the inner product. And then I need to multiply by psi as a function of t over here. Okay, let's just write the whole mess in there. 1 over root 2 times the sum from n equals 1 to 2 of root 2 over a. Well, I guess I can combine those together. The root 2 over a combines with the 1 over root 2 to just give a 1 over root a, right? Times the sine of n pi x over a times e to the minus I E N T over h bar. That's our psi at time t. And then we're doing an inner product here, right? Here's this function of x, here's this function of x, and we need to integrate with respect to x. And now we got to look at that mess and say, well, what can I actually carry out the integral a little bit? Well, a lot of this stuff is just constants that can go out in front. This doesn't depend on x. I can pull that out of the x integral, right? And these two constants, let's pull those out of the x integral and see what we have left. 1 over the square root of 2 pi h bar a, combining those two constants, times e to the minus I. Oh, this can't pull out of the sum, so I have a sum from n equals 1 to 2. And then I have something that depends on n, e to the minus I E N T over h bar. None of that stuff depends on x. And then the x integral is the integral from minus infinity to infinity of e to the minus I px over h bar times this sine of x. And I'm going to write the sine of x out using Euler's formula because that's probably the easiest way to do this integral. If I write everything in terms of exponentials, then I'm just going to have two exponential integrals. There may be a different way to do it as well. You know, you could certainly write this as a linear combination of sines and cosines and use your sine and cosine integration techniques. But let's just try it. Sine of theta is e to the I theta n pi x over a minus e to the minus I theta n pi x over a divided by 2I. I'm going to put that constant out in front. I've got another 1 over 2I out here. And I need to carry out this integral with respect to x. And now I can just divide it up into two integrals, and each one is going to be a combined complex exponential kind of integral. Should we do one more step on that, and then probably once it's clear how to proceed, I'm going to erase our stepping stones up here just so that it's clear for those who are on Zoom. This then is equal to 1 over 2I, 1 over root 2 pi h bar a times a sum from 1 to 2 times e to the minus I en t over h bar for the appropriate ens. And now for the integrals, I got to do two integrals, right? The first integral I have to do is the integral from minus infinity to infinity of e to the I n pi x over a n pi over a minus p over h bar all times x dx. Tell me if I'm making a mistake here. That's this integral. And then I've got to subtract off another integral of e to the minus I n pi over a plus p over h bar x. Did I drop anything there? And then those are just nice, straightforward exponential integrals, right? So I'm going to get, a 1 over this junk in the denominator, including 1 over i's. And those 1 over i's are going to cancel out this 1 over I. So there's some simplification to be done. But in general, there's not, as far as I can see, a whole lot more you can do other than completing those integrals. And I'm sorry, my integration limits are wrong here, right? This is my psi of x in 0. I shouldn't be integrating from minus infinity to infinity because it only has this value between 0 and a. That's a mistake, right? The infinite well wave functions are not signs everywhere. They're only signs between 0 and a, and there's 0 everywhere else. So I should really just be restricting the integration range from 0 to a. That doesn't really change any of the work we've done so far, but those integrals should be from 0 to a. And you could do the integrals and get something explicit. It's not going to help you a whole lot, I think. Questions on that one? It was just an example I was doing where you actually could carry it through, but it's still kind of a bit of a mess. We're going to get, once we integrate with respect to x, notice that we're going to get an explicit function of momentum. The x's are gone, and what we'll have is a function of momentum. There's also some time dependence in there. So what we've got is a function of p and t. That's what we're solving for here. And then finally, to answer C, the probability of finding, if we make a momentum measurement, what's the probability that we find a momentum that's positive, not negative? That would be the integral from p equals 0 to infinity of what I want here is rho of p, and we know now that that's the magnitude of phi of p at all different times t squared. Integrate over that range of momentum. the integrand is going to be such a mess that I'm not going to even attempt to go there. But that's, you're seeing some of the process that we go through, and that's the important part here. All right, questions on that? All right, good. I think that's the end of my notes on section 3.4. Now, before tomorrow's class, you're supposed to read 3.5, which is actually a pretty short section. It's on the generalized uncertainty principle. But I want to spend the remaining time just sort of setting it up, and then we'll remind ourselves again about it tomorrow. Griffiths does the derivation of it, and it's not, to me, especially enlightening. So I'm not going to talk about the derivation, but rather just write down what he gets. We know the uncertainty principle. The uncertainty principle has something to do with the product of the uncertainty in X and the uncertainty of P being greater than or equal to H bar over 2. Now we're going to do it for other dynamical variables. So here's the generalized uncertainty principle for the uncertainty associated with some dynamical variable A times the uncertainty associated with some other dynamical variable B. Those are like different Q's, right? We're assuming they're associated with some Hermitian operator. The way Griffiths writes it down is in terms of the product of the squares of these has to be greater than or equal to. Well, the first thing we're going to do is take the commutator between those two operators. And then for whatever state that we're in, right, these uncertainties might depend on exactly the state that we're in. So the product of the uncertainties might depend on what state the particle's in, what your psi is at that particular time. Then we're going to take the expectation value of that commutator, right? Commutator of two operators is an operator. And we can take the expectation value of an operator, way back when we said sandwich that operator between psi star and psi and integrate. So that's an expectation. You need to know what your psi is to calculate this expectation value. And then we multiply by 1 over 2i, which seems totally ridiculous. And then we take the square of that. Okay, so this is called the generalized uncertainty principle. So we'll show in just a second that it reduces down to the usual thing for the product of the uncertainty in X and PX. We know it's supposed to be greater than or equal to H bar over 2. We'll see how it simplifies down to that. Now, to me, it's somewhat unfathomable that Griffiths doesn't, we've got a squares on both sides. Why not square root? And, there's not too many complications because sigma A is non-negative, right? These uncertainties are never negative numbers. They're never imaginary. They're never complex numbers. They're always non-negative real numbers. This could be as small as 0, but generally it's 0 or positive. Same thing for sigma B. So if we want to take the square root of both sides, we really can without thinking too hard to get us something that's at least more familiar from the usual uncertainty principle. The product of the uncertainties has to be greater than or equal to, well, you see, we got to be a little bit careful because we might have some i's in here that are being squared. So the best way to take the square root is to take the absolute value of 1 over 2i times the expectation value in whatever state we're in times the commutator between those two variables, all absolute value. So that to me, I don't know why Griffiths leaves the squares in there because he doesn't want to write the absolute values. Just seems to make it more conceptually complicated. Okay, so let's do some examples and then we'll call it quits. First of all, of course, the very first example we want to work on is sigma x times sigma p. So let's interpret that here. Sigma x, sigma p. Maybe we'll leave it in Griffiths form. We'll take the square root at the end. How about that? Okay, so we've got a square of 1 over 2i. That's sort of weird to have that there. times the expectation value, depending on what state we're in. And we're going to find out that it doesn't matter what state we're in for X or P, but for some other variables, it will depend on the state you're in. So it turns out this expectation value doesn't really have a whole lot of effect in this case. Commutator between X and P. Remember, there's always some uncertainty in, when I want to find this product, this should be symmetric, but this isn't symmetric, but we're taking the square of it, so any minus signs will go away. Doesn't really matter which way you put the operators in there. Do you remember the argument for the commutator between X and P being H bar, I H bar? I'm sorry. Commutator between X and P is I H bar. Maybe it's best to remind ourselves of that. How do we find the commutator between two operators? Well, what this means is X, well, always when we want to find a commutator, we apply it to a function. Because if you don't, you're just going to forget some terms when things are operating. Okay, and then we write out what the commutator means. The commutator means X hat P hat minus P hat X hat, all operating on f of X. Okay, let's write out the two terms by themselves. In the position representation, the X operator is just multiplication by X. The momentum operator is minus I H bar ddx. And if I distribute this through, that's operating on that function f of X. Minus P, which is minus I H bar times ddx, operating on everything that comes to the right, which is X times f of X. That's why you need that function f of X in there. Otherwise, you'll forget to do a product rule that it really means. When we've got an operator operating on some stuff, it operates on everything coming to the right. So I need to do a product rule. That was something that didn't happen on some of the exam one, but since we're seeing it again here, it's a good time to review it. Oh, and that should be a closing parentheses there. Okay, so let's just simplify some stuff. I have a minus I H bar times X df dx. Here I've got a plus, if I do minus minus. I've got an I H bar there. When I take the derivative of this, I can do the derivative of the first function, which is 1, times the second function. That just gives f of X, plus the derivative of the second one times the first one. And the first one is an X. So X times the derivative of f with respect to X. That's the product rule there. And then you'll see I have a minus I H bar X df dx, and I have a plus I H bar X df dx. So, this part cancels against this part. And what I am left with at the end is I H bar times f of X. So this commutator operating on f of X is I H bar operating on f of X. And so we conclude that that commutator is multiplication by I H bar, right? That's how it operates. Okay, let's put that in there. Now, when I take this expectation value, you might worry, okay, well, we better use a particular function. What we do is sandwich this in between whatever our psi star and psi are, right? And integrate. This constant will just come outside the front of the integral. So it'll be this constant times the integral from minus infinity to infinity of psi star psi. And the integral from minus infinity to infinity of psi star psi, if we have a normalized wave function, is 1. So this whole thing is I H bar. And now you see the wisdom, or at least the sense making, of dividing by 2i here. Anytime you have a commutator between two Hermitian operators, you're actually going to get something that is called an anti-Hermitian operator. And if it's a constant, it will always have an I out in front. And so that 1 over I will cancel it out. So you really need that 1 over 2i. Not that we explained where it came from anyways. But this is h bar over 2, which is then being squared. So this whole thing is h bar over 2 squared. And then if I take the square root of both sides, I get the usual old uncertainty principle. Sigma x, sigma px is h bar over 2. Now let's compare this to another case. That case didn't depend on the state we were in. Here's another one that's not going to depend on the state that we're in. Okay, so let me just write the upshot here and then we'll finish up. Sigma x, sigma px is greater than or equal to h bar over 2. That means there's really a restriction on the product of these uncertainties, right? If this one gets small, this one has to get large in order to keep the product bigger than a certain amount. It can't, we can't let one get too small because the other one's got to make it large enough so the product is greater than or equal to that. How about, but notice it's not also saying that it is equal to h bar over 2. For some states, it might be double that or triple that. It would be a very special state that gives it exactly equal to h bar over 2. And those were those traveling Gaussian wave functions we talked about way back when. They're minimum uncertainty functions. Let's try a more trivial example. What if I want to calculate sigma x, sigma x cubed? This is the operator that in the position representation just multiplies by x cubed. Now you can imagine, what's the commutator between x and x cubed going to be? It's going to be 0. Because x and x cubed, they multiply, you can switch them around any order, it doesn't matter. So when you subtract them in the opposite order, you're going to get 0. Doesn't matter if we put that function f of x out to the right of it. So this commutator is 0. So the expectation value is 0. I can factor a 0 out of the integral. When I square it, I get 0. And therefore, when I take the square root, I get this. Now contrast those two statements. This one is really a restriction on what these can be. If one is too small, the other one's got to be big enough to make the product greater than or equal to h bar over 2. What kind of restriction is this? It's 0 restriction. It's not telling us anything. In other words, when we find this out, we get 0 information about this because we always know that this is a non-negative, sigma can't be negative, right? It's a standard deviation. This is non-negative. When you take a product of two non-negative numbers, you get a non-negative number, and that's all this is. We already knew that. So it's giving us 0 information. When you have the commutator of two operators be something that is non-zero, we call those two operators incompatible operators. That means you can't know complete information about both dynamical variables at the same time. We can't be in a definite position state and also be in a definite momentum state. In this case, this is what is called a, I'm sorry, am I using the right word here? Yeah, incompatible observables. So these are incompatible observables. I cannot find a single state that's in a definite state of both x and p at the same time. These are called compatible observables. They're Hermitian operators. They correspond to physical observables. I can measure x and I can measure x cubed. Well, to measure x cubed, you can just measure x and cube it. Sort of a trivial kind of operator. Compatible observables means you can be in a state that has a definite value of x, so only one non-zero probability, and a definite value of x cubed, only one non-zero probability, right? So in this case, when you have compatible observables, the uncertainty principle, generalized uncertainty principle, tells you 0 information. There's sort of an intermediate case between these. Notice what's simplified here is that this ended up being a constant. It didn't depend on what state we were in when we took this expectation value. It was special that we got a constant here for this commutator, and we could factor that out of the integral that was this expectation value, and the remainder integral was 1 because we had a normalized wave function. In general, I will get something that is not a constant operator here for other kinds of operators, and we'll do an example next time. If I get something that is not just a constant operator, there's still incompatible observables, but then this expectation value will depend on what exact state you choose. And so exactly what number goes over here depends on the state you're in. It might be a big number, it might be a small number, it might go to 0, depending on exactly what state your particle is in at that time. So it's sort of unusual that for this to be true, we don't even have to specify what state it's in. Generally, for the generalized uncertainty principle, you have to say what state you're in.